Hi, in this video, I will introduce a new combined thermodynamic cycle designed for offshore facilities using ocean thermal energy conversion (OTC) technology. In line with the guidelines from the COP climate conferences, this combined cycle partially addresses several issues, such as improving the efficiency of this technology, avoiding the need to connect offshore facilities to the public power grid, reducing the need for cold water pumping over long distances to supply coastal installations, and enabling islands, whose cold water sources are far away, to benefit from this technology. This innovation aims to make OTC accessible to all countries with maritime access. I will also mention a coastal country outside the intertropical zone, like Morocco, which could fully benefit from this technology if adequate infrastructure is put in place. The patent application for this combined cycle is now available on PatentScope as of October 31, 2024. Here is a screenshot of the summary with all references for those interested in the technical details. Historically, OTC has been confined to equatorial regions due to the requirement of a temperature difference of 20 degrees Celsius between surface and deep ocean waters. However, with this innovative combined thermodynamic cycle, this technology can now be deployed in any country with maritime access such as Morocco. This combined cycle opens new possibilities for harnessing ocean thermal energy on a global scale, significantly transforming the global energy landscape. Our planet faces major energy challenges. Energy demand continues to rise, while fossil fuel resources are dwindling, and their environmental impacts are increasingly concerning. The continued use of fossil fuels significantly contributes to greenhouse gas emissions, which are the primary drivers of global warming and environmental degradation. Gases such as carbon dioxide and methane trap heat in the atmosphere, leading to rising global temperatures, extreme weather events, and sea level rise. The conferences of the parties, COP, held under the United Nations Framework Convention on Climate Change, UNFCCC, have repeatedly emphasized the need to drastically reduce greenhouse gas emissions and adopt sustainable energy solutions to curb global warming. The COP conferences have called on nations to invest in renewable energy and adopt clean technologies to meet the goals of the Paris Agreement, which aims to keep global temperature rise well below 2 degrees Celsius above pre-industrial levels. The invention of a combined cycle for equipping offshore OTC installations represents a major technological advancement toward accelerating this technology's deployment. This combined cycle is more efficient than existing cycles, offering more than a 50% improvement in efficiency. To address challenges such as connecting offshore stations to the public grid, managing cold water pumping at coastal stations, and expanding OTC technology to all countries with maritime access, the invention proposes a two-step approach. The fifth step is the offshore stage. This stage involves deploying several high-power floating OTC platforms carefully distributed in equatorial regions, where each platform is surrounded by warm surface water and cold water located 1,000 meters below. Cold water supply to each platform would be ensured by pumping through a sufficiently wide diameter cold water pipe, CWP, to minimize pressure losses. Each platform would be equipped with the necessary devices to meet the combined thermodynamic cycle requirements developed by the invention, which differs from and is more efficient than currently used cycles. The combined cycle consists of two cycles. A. The first is a closed-loop organic Rankine cycle comprising two isothermal processes and two adiabatic processes. This cycle includes the following equipment, connected by pipelines forming a closed circuit, a high-pressure pump, a high-pressure evaporator, a steam superheater, a high-pressure turbine, a condenser, and a medium-pressure reservoir. B. A second cycle, which is a closed-loop trilateral flash cycle comprising in order the following equipment connected together by pipes forming a closed circuit, a two-phase twin-screw expansion, a low-pressure reversible evaporator which I call an isothermal container, containing the phase change material, MCP, a low-pressure steam superheater, a compressor, a desuperheater, a medium-pressure condenser, a medium-pressure tank containing the working fluid. This new combined cycle would improve the efficiency of the heat engine by more than 50%, and would convert sensible thermal energy stored in the oceans into latent thermal energy, stored in large insulated containers. Thermal energy storage would be ensured by freezing phase change materials with very low freezing points to very low negative temperatures. The term insulated container carrier refers to the low-pressure evaporator containing the phase change material to be frozen to store thermal energy in a concentrated manner in the form of latent energy. This insulated container built and mounted on board a boat or barge, has the particularity of being reversible, which serves as an evaporator and condenser, rechargeable and transportable. It is this dual characteristic that allows coastal stations to be supplied with cold, essential to operate without resorting to pumping deep cold water. This is in fact the only way to fully exploit ocean thermal energy conversion technology for the production of electricity and for the desalination of seawater, and especially for countries located outside the equatorial zone. The second step is the coastal stage. This stage occurs in coastal OTC stations, where energy is produced using the isothermal container as the cold source, condenser, and local coastal water as the hot source, evaporator, regardless of its temperature. This coastal stage is not limited to the intertropical zone and can be applied in all countries with maritime access. Morocco is a country bordered by the Atlantic Ocean and located outside the intertropical zone, with the source of cold deep ocean water located very far from the coast, exceeding 100 kilometers. Morocco has an average annual water temperature along its Atlantic coastline of 19 degrees Celsius, which might suggest that it cannot benefit from OTC technology. However, with the combined thermodynamic cycle, Morocco could harness this technology provided that appropriate infrastructure, particularly coastal stations capable of receiving isothermal containers, is established. In this new configuration, the parameters change, assuming the freezing temperature of the phase change material is -35 degrees Celsius and the local surface water temperature is 19 degrees Celsius, the temperature difference between the two sources becomes 54 degrees Celsius. This significant increase in temperature difference would greatly enhance the thermal engine's efficiency, raising it to over 18%. This performance is a significant improvement over the previous efficiency, which was less than 2%. These results indicate that the lower the freezing temperature of the phase change material, the better the efficiency. Therefore, it is crucial to choose a material with a very low freezing temperature to store thermal energy in latent form. As previously mentioned, OTEC technology requires a hot and cold source with a minimum temperature difference of 20 degrees Celsius to operate a heat engine coupled to an electric generator. Thus, countries outside the equatorial zone, lacking these conditions, are compelled to import isothermal containers to exploit the benefits of this technology. Therefore, the construction of coastal stations becomes crucial to accommodate these isothermal containers containing the phase-changing material, which will serve as the cold source. For the hot source, local coastal water can play this role, regardless of its temperature. After the complete melting of phase-change materials, a significant amount of sensible energy remains available for use, creating opportunities for economic activities and job creation. Among these activities are desalination of seawater using freezing methods, which produces high-quality water at a low cost, as well as utilizing the residual cold for air conditioning systems, providing a sustainable solution for cooling buildings and infrastructure. Aquaculture, such as fish and shellfish farming, can also benefit from the favorable conditions provided by ocean thermal energy conversion (OTC) technology. Thanks to the innovative combined thermodynamic cycle, the deployment of ocean thermal energy conversion technology on a global scale is now within reach. This breakthrough opens the door for every coastal nation to tap into a vast, free, renewable, and inexhaustible energy source stored in the warm tropical waters. By embracing this technology, we can diversify our energy mix, reduce our reliance on fossil fuels, and significantly lower greenhouse gas emissions. Imagine a future where clean, sustainable energy is not only a possibility but a shared reality. With ocean thermal energy conversion, we are one step closer to achieving a resilient and sustainable world for generations to come. Let's make this vision a global commitment. If you found this video valuable, please share it to help spread the message. Embed it in your blog, translate it into your local language, or share it on social media to reach audiences worldwide. Together, we can drive the change towards a cleaner, greener future. Thanks for watching.